Hi, this is Roger from Kanka Labs, and today it's about AC measurements, voltage or current measurements. And as you can see, I've put three multimeters connected in parallel with the same source. They are all switched to AC mode and they all give three completely different values. Now, there is something very important to know. You might notice this cheapy one here. It certainly is not a true RMS multimeter. But here, these two, they both say true RMS multimeter as well as here, and they give totally different values. Now, of course, the reason is in what kind of signal I fed into them. And I'll tell you already the main difference. This one is true RMS, but this one is true RMS AC plus DC. And there's a big difference between true RMS AC and true RMS AC plus DC. While this one here only gives an average value of the AC voltage. Now, to investigate where this huge difference in the displayed values comes from, we'll have to delve a little bit into theory, but I'll promise you that in the end you will know why it's so important to have a true RMS AC plus DC multimeter, and how you can interpret the measurements of the three, and how you can know, if you know the shape of your signal, when you can trust the display and when you cannot trust the displayed value. So let's take a piece of paper and see what's the theory behind true RMS and true RMS AC plus DC measurements. So first let's take a look at what is the definition of true RMS. RMS is the abbreviation of root mean squares. We'll see in a minute what this root of the mean squares means. But the definition is that the RMS value is equivalent to a DC voltage that puts the same amount of power into a resistor. Now, let's suppose we have a voltage source that, of course, if we connect it to a resistor, it will send a current through the resistor. And now, what's the definition of power? Power is voltage multiplied by current. Now, we also have Ohm's law, and if we have a fixed resistor, we know that the voltage is also the resistance times the current. And now we can, in this formula of the power, we can replace either the U, the voltage, or the I, the current, and this gives us that the power can also be written as U squared divided by R, or I squared multiplied by R. And I call this is Ohm's law. You all know that because it's the first thing that you learn in electronics. And I call this one here Ohm's law of power. That's I think that's my own creation, but I'm probably not the first one to call it that way. And that is the second formula you should always remember, because it's after Ohm's law, it's the second most used formula in electronics. Now, if we know that that the power through a resistor is depending on the square of the voltage, that brings us one step closer to what root mean squares means. So let's take as an example a simple rectangle signal, and let's calculate what we get as the equivalent power that is calculated in this way. Now, for an example calculation, let's take one of the seemingly most simple waveforms. We take a symmetrical square wave. Symmetrical means that the off time has the same duration as the on time, which you also can say it has a P-W-M ratio of 50%. And now let's presume the square wave starts at 0 volt and reaches a peak value in the on state of 2 volts. Now, what does your intuition say? What is the effective or RMS value of such a square wave? Well, you would suggest, well, it's half the time off, half the time with 2 volt, so it must be 1 volt RMS, 1 volt effective, right? Well, let's make the calculation, and it's straightforward. If you have periodic signals, you only have to calculate one period, which means we only have to calculate the squares of the voltages for from here to here, and we only have to take the parts of the signal where the amplitude changes, which is quite simple here. We only have 2 areas with constant voltage, and we simply take the squares of the voltage. We don't have to calculate any resistance because we first square the voltages and in the end we take again the square root, so any resistance would cancel out. So here we have 0 volts squared, and here we have 2 volts squared, which gives us 4 volts squared. Now, to take the mean value of these two, we still have to multiply them with the part of the time, the relative part of the time that the voltage is present. This is also very simple here because it's a symmetrical square wave. Each part of the signal is present half of the time, so we still have to multiply each with a factor of 0.5. This of course gives us here again 0 squared volts squared. Here we get times 0.5. Here we get 2 volts squared. So now we have to sum up the weighted squares. Why are they weighted? Because we have multiplied them with their relative time, or with their relative part of the whole period, and we get 0 squared plus 2. This gives us 2 volts squared, and now we have to take the square root of this sum, and the square root of 2 volts squared is not, as we thought from intuition, 1, but it is the square root of 2, which is around 1.41 volts. So when it comes to calculating the effective or RMS value of any AC signals, you can't rely on intuition. You have to do the calculation, and this is quite a beginner's error or trap, that you think you can easily calculate the RMS value of square waves, no matter if they are symmetrical or non-symmetrical. Don't rely on intuition, just do the math. And now if we repeat the algorithm that we used, we now also can see why it's called RMS. First we took the squares, then by adding up the squares weighted by the relative factor, the relative time that they have from their period, that is nothing else but taking the mean. And the third step was taking the square root. And now you can see why it's called RMS. It's the root of the mean of the squares. So that's the explanation, and at the same time the algorithm that you either can use point by point on a complicated signal waveform to calculate the RMS, or your digital oscilloscope can do it for you, or an analog circuitry that does exactly this, squaring up the voltage, taking the mean, and then taking the square root of the mean. And that's exactly what analog ICs like 8636 or the analog devices 8736 or many others are doing on an analog basis. But you also can do it just on a piece of paper, at least for cases where the waveform is not too complicated. Otherwise you had to use more complicated math for that. So now let's calculate the RMS value of the signal that I fed into the 3 multimeters. Just to solve the secret, I took a square wave with an offset of 2 volts. So let's call it the starting value of the low point of the square wave is 2 volt, and the peak amplitude is 8 volts. And the square wave still is symmetrical. So we just only have to take 2 areas of interest into consideration. In this area we have a squared value of 4 volts squared, and here we have 8 squared, which gives us 64 volts squared. And of course, because it's symmetrical, we have to apply the factor of 0.5, because half of the time we have this value. So this is of course wrong. We have half of the time 2 volts squared and the other half of the time 32 volts squared. Now we sum it up again. This gives us 2 volts squared plus 32 volts squared, which gives us 34 volts squared. This is the mean. These were the squared values. And now we only have to take the square root, and the square root of 34 volts squared gives us, let's take the calculator, and this gives us 5.83 volts effective or true RMS. Now, and you already can guess that what I called in the opening scene True-RMS AC plus DC, We know that this is the correct value, and of course it's very important that your multimeter measures the absolute values, including any DC offsets. Now, what would we get if we simply put a capacitor in front of the multimeter? Then we get a different waveform, and you might from intuition think that that doesn't matter if we have a square wave of an amplitude of 6 volts, which goes from 2 to 8 volts, which looks like the one I've shown you. Or if we, with the capacitor in between, the voltage would vary, or the rectangle would vary between -3 volts and +3 volts. The signal has the same shape and the same amplitude. The only difference is the offset. Now let's calculate what we get here from this AC coupled signal, while this signal was DC coupled. Well, the first half of the signal we get -3 volts squared, and this gives us a square value of 9 volts squared. And the second half the same. Here we have +3 volts squared, which gives us also again 9 volt squared, and we again have to apply the factor of 0.5. And what do we get now? We get, these were the squares. Now we take the mean value by adding up the time-weighted squares. Time-weighted means we have to multiply them with the percentage of the time that the signal is at this level. And this gives us 4.5 volts squared plus 4.5 volts squared, which is again 9 volts squared. And now we take the root, and the root of 9 volts squared is 3 volts effective AC coupled. So there's a very big difference between the DC coupled RMS effective value 5.83 and the AC coupled effective value. There's nearly a difference of a factor of 2 between the two. And now you already can guess that this is the basic difference between the two multimeters, which both said to have true RMS measurements, but the simpler one and the cheaper one only measured the AC coupled signal, and this gives us a totally wrong value. And only if the multimeter is DC coupled and measures the correct or makes the correct RMS calculation internally, then you only then you get the correct value. And we'll verify this in a second with an oscilloscope. With a digital oscilloscope, you of course can also calculate with the math functions the true RMS value. So let's change our setup and let's change the camera to reveal the secret, how the signal really looks and what the oscilloscope says, and what the three multimeters say which is the correct value. So now we can see on our Rigol DS1054Z digital oscilloscope what the real waveform is. As I told you, It's a symmetrical rectangle signal, but with a DC offset of 2 volts and a total amplitude of 6 volts. It's to be honest, I cannot exactly set the offset 100% to 2 volts and 100% to 8 volts at the peak voltage, but anyway, that's enough for a comparison. And the nice feature that every modern digital oscilloscope has, it can calculate the true RMS value of any waveform and of any frequency just with its internal processor. And we get here an RMS value of, it jumps around a little bit. You probably won't be able to read it due to the resolution of the camera. It jumps around 5.76 volts, and that's within 1% of what the X-Tech Multimaster 570A says. And so now we know this one is really gives us the correct value, true RMS AC plus DC. We have calculated an ideal measurement result of 5.83 volts. Now the difference is not necessarily from inaccuracy of the multimeter or excuse me, or the digital oscilloscope. It's just because I cannot 100% exactly set the values of the lower value and the higher value to the values that we took for calculation. But anyway, we know this is exact, and both of these cheaper ones give a wrong result when measuring a relatively simple waveform, just a symmetrical rectangle waveform of only 1 kilohertz. So it's not an issue of too high a frequency that they couldn't measure it, but with a DC offset. Now, can we simulate, or can we get the reason for the difference is both of these have a capacitor in front of their measurement circuit, and the capacitor does this. It just it measures from a AC coupled signal, which gives us, as we know, a different value, which should be ideally exactly 3 volt effective true RMS AC coupled. And what does the Rigol say from its calculated value? It says 2.98, which is near enough to 3 volts. So we still have a deviation here of 10%. And now the old saying says you get what you pay for. Not only that, only the X-Tech with its true RMS AC plus DC measurement gives the correct value. Even for AC coupled signals, the result from the cheap Uni-T is 10% out of range, and that's really not very useful. So it's in a double sense of the meaning, well, not unuseful, but less useful than a good multimeter. It does true RMS only for symmetrical signals that are with a symmetrical to the x-axis, to the horizontal axis. As soon as you have a DC offset, it gives you a wrong value, and even here, where it should give you the correct value with a symmetrical signal, it's 10% out of range. And this one, which even doesn't do any true RMS calculation, but a simple averaging of the rectified signal, this gives you a wrong display because it's a square wave. Let's see what we get when we change to a sine wave. Just the push of a switch, and now we get a calculated value of 2.06 volt, and now Also, the cheaper one is at least with a few percent difference near the right value. But remember, this one, the cheapest one, gives you only halfway correct values for sinusoidal signals without any DC offset. This one will give you halfway correct values for also for different waveforms. Let's take a triangle. Let's see. The calculated value would be 1.68 and it displays 1.6. So still 8%, not 6% out of range. So that's way too much for a correct measurement. And only if we switch back to DC coupling, now the correct value is 4.93. The X-Tech gives you 5.16. And I even would trust the X-Tech a little more than the Rigol because the specifications are very good, at least much nearer to the correct value than any of the other two. Now let's for the end take a little way back to history. When I was a boy, the only thing I could afford was a simple averaging multimeter in AC mode. True-RMS was in the 1970s and 1980s, was absolutely out of the budget of a hobbyist. And oh, the auto power off has just switched this one off. Later, True-RMS multimeters became quite affordable. This one costs only around $40 or euros in this range. But you see, what was once a dream to have a $40 or 40 euro multimeter with true RMS capabilities, you have to know what you measure. It's not very exact, and it only works with symmetrical signals. And only modern multimeters with AC plus DC measurement, which are DC coupled, give you a more or less correct value. But perhaps the simplest way today is just buy a good digital oscilloscope like this really best bang for buck Rigol DS1054Z, which does the calculation for you for every waveform, for every frequency, and I think that's perhaps the best way today, but you don't always have an oscilloscope carrying with you. A good multimeter like the X-Tech should do the correct measurement. So that was it for a little explanation how true RMS is calculated, what you have to watch out for, and that true RMS is not equal to true RMS, depending on AC coupled or DC coupled. So I hope you liked it. I hope perhaps you could learn a little bit, and see you next time at Kanka Labs. Bye from Roger. Bye from Kanka Labs.